All right, let's go and see what the exercise 2 is all about. So it's about PWM and interrupts. So earlier we have gone through the PWM. Before that I actually introduced something about the timers, how to use them, and also the interrupts. And this basically just combines all of those. So after this you should be able to control any number of servos and also handle the interrupts from different sources. Okay, and this exercise you would need the prototyping board, of course, and then servo motor, preferably low power, SG90 or similar. I also found a good place where to find some data sheets for any sorts of servos, serverdatabase.com, and that actually shows, okay, this is 4.8 volts nominal voltage, and that has 25 ounces per inch, which means 1.8 kilograms per centimeter torque, which means that actually when the maximum torque here on this very small device at 1 centimeter long the arm, this would produce 1.8 kilogram load, which is actually quite much. So don't put any sharp object at the end of it. It will be owie. Okay, it also says how fast it can go. 60 degrees in 120 milliseconds. That's quite moderate, but that's enough for small toys, which is the main target for this. Dimensions are there, weight, okay. Actually that this is so-called 9G servo, which means the weight of the servo is 9 grams. Dimensions are there, motor type, okay, gear type, and that kind of stuff. And okay, gear type is plastic, which means that okay, you can always destroy plastic parts by loading them too much. Pulse width, okay, 500 microseconds to 2400 microseconds. That's the full range, which gives you about 180 degrees. If you take a look at this review of the Tower Pro, there are plenty of different all variants. Some has just got it working fine. Some had a really much bad to say about it, but that okay, this chatter here, I know where it comes from. It comes from the jitter of your signal or too short pulse period. Okay, but anyways, as you can see, this is not a mark of high quality product if you have plenty of great and plenty of not that great great. Okay, but anyway, some data is available. The pinout you can actually also find, but okay, I can show you it on my camera window. There are 3 wires on these triple things, and this center wire is a red one, and it's always the plus the positive power supply. Then this one has brown ground wire. Okay, sometimes it's black, sometimes it's some other color. But then basically, well, it can be black, or I have seen actually blue or some and something like that. If you have some weird color next to that on either of those ends, you should actually take a look at if you can find the real data sheet for the device. This is very cheap. I just buy this and guess the wires. It doesn't break if you basically connect it wrongly, since the center wire is power supply, and in order to power to flow you need ground. If you mistake the ground, then actually it doesn't do much bad, since the current is not flowing. But anyways, this has the center red wire is the positive power supply, in this case 5 volts. Then we have this brown, which is the ground wire, and then the PWM signal should be on this orange wire. Okay, setup. You can read it. Okay, I need to check something here. 1.6, pin 1.6, that's fine. So PWM output should be connected to pin 1.6 to control servo motor. Okay, and this actually also says create a new project from the previous template. So take the last exercise, exercise 1. Oh, wow, that's not a good name for it. I think this is much better. Okay, rename the project, and then actually there are also instructions. Open exercise 1 project, save it as a template, then create a new project from previous template, and so on. Clear main code on forever, and basically you can read it from there. PWM signal, output signal should be on pin 1.6. Okay, add a clock for PWM usage, of course. I'll show you how to do it. Make real connections only until you are in a point that you want to test the system, just in case. So make sure that your code has even a chance to work before you take the PWM, the real servo, since this takes roughly 100 milliamps of power in maximum in any case. So it will be safer that way. Task: design a system control the movement of the servo based on PWM component, and basically the system should change the position of servo on each button press. So there is that user button at port 2.2, and when you press it, it should change the position. And initial position is a neutral, meaning 1.5 millisecond pulse width, and each button press causes a servo to change the position, and minimum of 5 different positions. You can decide also to have more positions there, even some are arbitrary, not necessarily on the order. And a couple of other things. Since this is about interrupts, button press must be detected using interrupts. Okay. Let me take that one out by the software. So switch bounds. Now we are actually having a mechanical control and using a simple switch. So I would say this is a kind of critical that you have a debouncing mechanism for the switch. Okay, there are some, actually there is a debounce component that you can use to solve the problem. But that's basically, as long as it does not take more than one the press each time I press the button, then it's okay. There are several different ways to do this. And then, okay, to get maximum point of this from this exercise, the servo must change the position smoothly. And this can be done by the interrupts. I actually showed you that this animation here. And practically you need to change the pulse width smoothly, not by jumping it. Okay. There are some hints there, and okay. And again the hint, do not try to do all functionalities at once. Do it first, for example, that you are sure that your button interrupt is working, that there you can use actually that blinking LED light to check that you have a button there giving interrupts, and then that you can actually interrupt more than once. Okay, that could be the case. If you don't clear the interrupt, if it's required, then basically you are in trouble. Okay, and next step would be to start working on the PWM. Make it first 1.5 millisecond pulse width and 20 millisecond the period, and when you have that one on pulse on the port output, then you can actually hook this servo to the right pins. By the way, hooking the servo, I do it this way. I'm just using extension wires, and I do actually have the on my board I have this nice it has both male and female connector on each pin, so for this exercise this is just perfect. So I have just extension wires to spread these 3 wires, and using the same color coding, and now it's quite easy to find the correct pins. This PSoC board actually have the power and ground on the ends of the connectors on these corners, which is quite nice. Okay, so that's the what the exercise is all about. Next I will show you the how to actually configure a PWM device. And let me start actually from this yesterday, or well, the previous exercise. I will make this as a template. Okay, templates is done under the project. Say copy to my templates. I already have done it. Then you close the workspace, create new project, same target, good, my template projects, and I have that template project here. Next the file, the project name. What was the project name I would want it to have? Okay, that's the project name. First name, okay, maybe I'll just put the login ID here. Not that one. There. Okay, and finish. And first I will be doing actually, I will just remove everything from the scratch. You can leave there on the design whatever components you think you need. Let's see, maybe I can actually still use the I don't think that I would be using Word. Blue LED I would be using, then you also would have the button pin there. So whatever you have there, you should leave. I will also put that digital input pin. Then of course check the pins for 2.2 button there. Generate application. Okay, main.c actually, okay. So practically something like that. Actually you might also add here, just for fun, that this is PSoC design course exercise 2. Okay, so that's the starting point. Compile just for fun. And now let's take a look how actually this PWM is working. I'm just searching it, PWM. Okay, there's the component. There we go. Ha. Excellent. So I have a PWM, the component. It requires clock and of course parameters. But let me start by adding a clock. I'll just add a clock, since this way you can get these tool. The tool actually will help you on the pulse width generation and also the period generation. So there we go. Clock 1, it's a new, and let's make it, for example, just for fun, 10 kilohertz. Clock like that. And now when I open this one, I can already see, oh wow, I got lucky. So basically, okay, let's see, PWM, okay, it's 8-bit UDB, uses universal. Okay, it automatically gives you 2 outputs because, well, this actually allocates resources so that you can run a dual PWM control which is synced together. But our case, we actually need only one. Actually, that the dual is just quite nice, since then you could, for single component, you can actually control 2 servos, for example on artificial finger or something like that, or robotic arm. You have at least two servos there, or counter servos that are pinching something to in between. So basically like that. You could go to 20 milliseconds. oops, 20 milliseconds period, and make the compare value actually 15, which gives you, okay, I think this gives you 15 millisecond pulse. Oh, not 15, but 1.5 millisecond long pulse. So this would already set this servo into neutral position. Okay. However, how smooth you think this is, since then you can actually think of the 500 microseconds to 2.4 millisecond range. And in order to have a smooth operation, actually you would need more bits. But I will let you to decide on your own numbers. But this is your design overall, after all. Okay, so that actually gives you the control for this servo. Okay, let's take another thing. So this is just basic functionality, which should actually come from there. And then enable mode software only, good. Run mode continuous, good. Trigger mode no, none. Take a look at the exercise, this data sheet of this component for more advanced stuff. Capture mode none. Okay. Interrupt. Okay. In order to turn on the interrupt, actually you can select here. Oops, not none. Either interrupt on terminal count, meaning when this 200 ticks expires, or interrupt on compare event. So practically it'll be the terminal count means that it's okay, restarting at when the count from okay, this period value runs down to 0, either here or the compare event. So practically if you are interrupting on terminal count, then if you change the value based on that interrupt, then you don't time actually to write it before it's loaded again. So basically you need to have this reload value, meaning this compare value written to this register before it's loaded, and the reloading happens in this terminal count always. So usually it's better to have the interrupt on compare one event. Okay. All right, then what else we need? We need an output for that PWM. So you need again digital output. And there, and then actually you probably want to call this one PWM out or something like that. And strong drive, good. Apply. Okay, so now we have the PWM going there. Okay, interrupt means that you need also interrupt service routine. Let's add interrupt service routine there. This is the way to generate all that pre-written raw code, and then basically just click generate application to get this application programming interface. Okay, the rest of the exercise you can do yourself. You have probably done similar exercises already on the previous microprocessor courses. This is not much different, except that you have more pre-written code and more power for the device here, maybe. So next step, write your code. Okay, and then one hint, this is supposed to be an interrupt based system, which means that basically you do not check any status of any register here. You just basically use ISR, oops, okay, sorry, use interrupt service driven these flags, global flags, semaphores, as a signaling that an interrupt has been served. And basically then on the time consuming calculations and such, put it on this for loop, but short things that you read and write values to the registers, that you can actually do on these interrupt service routines. So that will give you make you a efficient code. Okay, so that's all for this chapter 2. All for the chapter 2, which was about timers and interrupts, and application here is PWM and servo motor control. And exercise 2 actually is exercising the interrupt service code writing, and then the using of timers as PWM the device. Okay, just one small detail about this PWM device. This is practically same as timer. Let's take a look at what is the timer, what is the difference here. So timer, it has terminal count or interrupt, it has clock input, reset input. So PWM actually only, the difference is that it also has the compare value. So you can write a value to a register which is compared to the current value on the counter. So not much difference. Actually, let's see, is there a, okay, this timer here does not have the this compare function inside. So, but anyways, practically PWM is using a countdown timer and free running timer with a compare value. Okay, there we go. I hope I didn't add any confusion. Okay, so next topic would be data acquisition. But before that, you need to do the exercise 2. and the deadline for returning it is April 22. By the way, I might actually change these return dates at some point. So if this one shows different date that is in this video, don't worry, you always follow whatever is written on this web page.